Hello, welcome to a video on geometry of numbers. In this video we are going to discuss an application of Brisfield's theorem. This theorem is named 9.5 in the 9th chapter of Geometry of Numbers, the book written by C.D. Owls. The statement of the theorem is: suppose a Minkowski's M set centered at the origin. A Minkowski's M set centered at the origin which is named O has area 4 times A. 4 times A is the area of the M set. Then the M set contains more than the number A in square bracket minus 1, and this is the number that stands for, if A is a real number, this number is the integer which comes just above the real number. That is the we can say that it is the ceiling number. So the ceiling number, the ceiling function, it stands for the ceiling function. That number minus 1, that's A in square bracket minus 1 pairs of lattice points other than the origin. Let's come back to let's come to the steps of the proof. Suppose M be a Minkowski set having the given properties, having the properties stated in the theorem. But first we begin with the given that M set as stated in the theorem. Its area is 4 times A. Area is 4 times A, but related to that we have to take an M set. So the given set has area 4 into A, but related to that M set we have to take another M set. Its area is equal to A. How these M sets are related can be understood only referring a figure. So for we are going to explain it further clearly, we are going to a figure. See the figure. Okay, before we have to consider one more figure, and in this figure you can see, and this is the M set. In the beginning we are given an M set, its area which is drawn here using red color, and its area is 4 times A or more, 4 times A or greater than 4 into A. So let's again refer again the statement. It has area, suppose which is centered at origin, has an area 4A. It is stated that it is 4A. 4A is the area. Okay, then exactly it is 4A area. Now and so we take the M set having area 4A, but we suppose we reduce that M set by that M set is reduced in measurement, in its one-dimensional measurement it is reduced to half of its half of the original M set. The red colored M set is the original, and we take the original M set and its dimensions are multiplied by 1 by 2 to obtain the small M set. Hence its dimension is reduced by half. It is reduced by, or it is reduced to half of the original dimension. What happens to its area? The area of the original M set is 4A, and the area of the reduced M set can be then 1/4 of the original area. So 1 by 4 into 4A, which cancels 4, and we get that the area of the small M set is A. So this is the area of the small M set is A. Now Okay, now after that we are going to, after this we are going to translate this M set to a new position, so that we get a specified number of lattice points inside, which makes this translation makes it sure that we get a specified number of lattice points inside, applying some previous result, applying a previous theorem. And that previous theorem is theorem 9.1. So by applying theorem 9.1, we translate it to a new position, and which ensures that there exists a specified number of lattice points. But by chance, one of the lattice points may be on the boundary of the newly positioned M set. May be on the boundary of the newly positioned M set, but most of the cases this is not like that. So I mean, all lattice points may belong to the inner portion. It may be well inside the new M set, but in such cases, if it is on that boundary, you can continue with that. You can proceed using that point on the boundary. But if it is not the other case, that means if all lattice points are inside the boundary of, or inside the M set, newly obtained M set, then you can adjust that lattice that M set. You can slightly translate it further to obtain one of the lattice points on its boundary. So until you get one of the lattice points on its boundary, you go on. You keep going. Going by translating. You can keep going, translating the M set further. Thus, now we are at a position. We have now reached a position that we have a lattice point. We have an M set. We have an M set, and that M set contains at least one lattice point on its boundary. So at this position, at this point of proof, now we have a major step to take, and for that you can refer the figure. One more figure we have, and this is that figure. So consider this M set, and the new position of the M set will be named M prime. The new position of the M set will be M prime. Now we can compare once again. We want to go back to the original, the first figure. So this is the second figure. In the second figure we have this M set, and this is the M set that we have obtained in the latest position. We have obtained in the latest position that M set. So we can see that. And this is that actually this is not that M set. It is further translated to obtain that M set M prime, which is named M prime. But the area of this M set is same as that M set M prime in that second, which you can see in the second figure, M prime, and also it is equal to the area of this area of the M set, which is smaller than the original M set. That is the reduced M set. So all these M sets have the same area. Only that is the point I want to make now more clear. Okay. And then we will then come back to the original form of the M set. We will finally, at the end of the proof, we will come back to the original M set. So, but before that, all the descriptions will be based on this reduced M set. We are now going further. We are going to explain further on some activities. We are going to do some activities with the reduced M set. And after that we will come back to the big original M set. So okay, coming back to this here, now we have that M set. That M set has the property that it has one lattice point on its boundary. That way we have taken this M set M prime. and m prime, and also you can take the you can note the center of the m set. Let O prime be the center of the m set. So m prime is the m set, and O prime is the center of the m set, and let's take P as the point on the boundary of that m set. Now we can join the line O prime and P, and this line is joined O prime and P, and it is further extended. It is extended further in the opposite direction as we construct it up to P, and it is further extended, and the same length is measured in the opposite direction to get a point. The length measured is equal to P and the length between O dash and O prime and P, and this length is measured first, and the same length is measured in the opposite direction to obtain another point. That point is O double prime, and based on that point or about that point, we are going to take a copy of the m set, or we can say that we are translating. We can translate the m set m prime along the line, so that its sender moves along this line, and further it reaches. It is continued. The translation is continued until it reaches the newly obtained point O double prime. Thus it sits there, and it is not further moved. When as it reaches the point O double prime, it is kept there, and now you can see that this is the position of the two m sets, and the new m set will be called m double prime. So this picture now shows those two m sets. After that, but one more thing is very clear, that the point P is now the center of the line segment O prime on O double prime, and O prime is the center of the m set m prime, and O double prime is the center of the m set m double prime. But see, we can take P. We are now focusing. We are going to focus at the point P, and this point P is the center of the line segment joining O prime and O double prime. About this point, we are going to define. We are going to take an m set. We are going to take an m set m triple prime. We are going to take an m set which is a bigger m set m triple prime. But before talking much about that new m set, we have to talk about an m set which is not visible in the figure, which is not given in the figure. In the figure, it is not given because to avoid confusion. In order to avoid confusion, that figure or that m set is excluded. That m set is it is obtained by expanding the m set m prime. See, take the m set m prime, it is then expanded. It is expanded keeping its sender without changing its sender, keeping its sender, or the new m set. After expansion, we get a new m set. That m set will have the same sender. It will have the center at O prime, but that m set, the big m set, is obtained by multiplying the dimension of m prime by 2. Means all one dimensions of m prime will be, one dimension of m prime will be multiplied by length in all directions will be multiplied by 2. As a result, you are going to get its size multiplied by 4, or having we get a new m set having its area multiplied by 4. So that m set for the time being, let's call that m set m double prime. It will also be called m double prime because it has the area 4 times that of its area is 4 times that of m prime. But what is the area of this set m prime? Area of m prime is a. It's because we have it is clear from the way we have defined m prime. you can go back to the steps, and you can go to the initial part of this proof. You can see the method or the procedure to obtain the m set m prime, and from that procedure it is clear that area of the m set m prime is equal to A. And now this m set is expanded to obtain a new m set, a bigger m set with the same center, but its one dimensions are multiplied by 2. As a result, its area of the new m set is 4 times that of the m set m prime, and so its area is equal to 4A. And after that, even though that new m set is not given there, and you can think about that, you can just imagine about that, and that m set since it has the center at O prime, it is going to be translated along the line. See, that m set will be translated along the line O prime P. O prime P. Along this line it is translated until it reaches, its translation is continued until the center moves to the point P. When it reaches P, it is kept there. And at this position, that bigger m set will look like this. And this is the picture of that bigger m set when it takes the position, when its center takes the position at P, at the point P. So what is the area of the m set? This is m double prime. Okay, sorry, m triple prime. Actually, mistake. There is one more dash must be, quotation mark must be there. So m triple prime it is. I have to write here m double prime, m triple prime. So this is the outer m set, and its area is then 4A. Area of this is A. Area of this m set is A, but area of the big m set is 4A, which is obtained after translation. Okay, then we can now. We can then see that. Okay, let's now come back to the steps of the proof. Okay, after that, so starting from the beginning. Okay, I haven't explained that the steps. So these are the construction part of the proof. I have given you an idea about the main constructions, that can geometrical constructions that can be used. That is useful for developing the steps of the proof. Now we can go through the steps of the proof. And suppose M is a Minkowski's M set of area A, and okay, and this is here. The point mentioned here is about the Minkowski set. It's about the Minkowski set taken here, the reduced Minkowski set. From there we continue. Okay, and so actually in all the figures that M set is marked as or named as M prime. Okay, and you may avoid that difference. Okay, that mistake here, M prime. Okay, let's call this M prime. Let M prime be a Minkowski M set of having area A, and let A be any real number. Let A be any real number such that n minus 1. Okay, here given A as a real number. Let A be any real number. Nothing is mentioned more about that. A is any real number. We can just assume that as it is given in the statement of the proof. We assume that A is any real number, but you can find two natural numbers or two positive integers can be easily. So any real number, but since it stands for the area, it's positive real number definitely. A is a positive real number. Okay, and also since A is a positive real number, you can find two natural numbers n minus 1 and n. such that this condition is satisfied, n minus 1 is less than, or you can find two natural numbers, one natural number just below and the other one just above. So then it satisfies n minus 1 is less than a less than or equal to n. Now apply the theorem 9.1. Applying the theorem 9.1, we can translate the M set to obtain a position of it and that contains n lattice points. Yes, applying then using the theorem 9.1, and then when we apply that theorem 9.1 on this set, it is then translated to obtain a specified number of points, lattice points, and those lattice points, how many lattice points are there? You can obtain n lattice points in that new position of the M set. And now, as I have earlier explained already, I have explained. Then you can further translate it slightly. You can translate it to obtain one of the lattice points on its boundary. So we can say that there are n lattice points either inside or on its boundary of the new position of the M set. New position of the M set. The new M set is then slightly translated to get one of the lattice points on the boundary of the new set, and let the center of the new set be O prime, and we join O prime to P, and P is the point where P is the point on is the lattice point on the boundary. Next, we extend O prime P to O double prime, so that the distance O prime P equal to O double prime P. We construct an M set M double prime. We construct an M set M double prime having the same size that of M prime. See, and there the name is correct, M prime, and the center at O double prime as shown in the figure, in this figure. Okay. And if Q dash is a lattice point and now we are going to look at specifically on lattice points present in M prime and M double prime. So if suppose Q prime is a lattice point on M prime. Suppose Q prime is a lattice point on M prime, and then there will be a corresponding lattice point Q double prime. There will be a corresponding lattice point Q double prime in M double prime. It's because of the fact that the translation is done on what the translation is done because the translation is done based on the point P, the lattice point P, which is present on the boundary of the M set M prime. So it is because of that. Okay, then we get that there exists. Okay, then there exists a lattice point Q double prime in M double prime, and vice versa. That means if there exists a lattice point in M double prime, then you get a corresponding lattice point in M prime. So the number of lattice points in M Q prime will be equal to the number of lattice points in Q double prime. Sorry, M double prime. Q number of lattice points in M prime will be equal to number of lattice points in M double prime. A mistake. I have made a mistake by saying that lattice point, calling it a lattice point. Now M set, actually it is M set. The number of lattice points in M set in both M sets must be the same. I mean, but one point is common to. There is a point which is common to both lattice points. So that is another important thing. The point P is but common to both lattice. One point which is common to both the sets, Minkowski sets, M prime and M double prime. But P is a common point which rests on the boundary. But a special case is there, but that special case requires special treatment. That is when the point q prime and q double prime is also, the point joining q prime and q double prime is the common boundary of the set of the sets m prime and m double prime. That can also happen. The line joining q prime and q double prime, the two lattice points q prime and q double prime, when that is the case when the lattice point q prime, the lattice point q prime which belongs to m prime, and the corresponding lattice point q double prime which belongs to m double prime. That can be when we join these two lattice points by a line, if that line is a part of the line joining q prime and q double prime, when it is a part of the boundary of the m sets. If it's a part of the boundary of the m sets m prime and m prime and m double prime, that's a special situation. That situation can also be treated in a similar way, but that needs special attention. Now we continue with that most common case where the most common case, that is only one point is. In that case, we have only one point P on the shared portion in the boundary. Okay. And we can now count we are now going to count the total number of lattice points belonging to the sets m prime and m double prime. And we can count that there are n minus one lattice points which are well inside the set m prime, and same number of lattice points will be there in a similar way in the other set m double prime. But plus, in addition to that, the one point, that point which belongs to the boundary of which is shared by both sets m prime and m double prime. So in total we have n minus 1 plus n minus 1 plus 1 equal to n minus 1 points, lattice points belonging to m prime and m double prime. And these are the lattice points which is covered by, and hence we can say that these lattice points are covered by m prime and m double prime. These are the lattice points covered by this. And then we enlarge. After that we enlarge m prime to obtain m triple prime and I have explained that very well. I have explained how to enlarge this and the procedure to enlarge it, and then the method to translate it to obtain the current position as shown in the figure. So I have since I have explained it, so I do not go for further explanation on that. Okay, and then it is positioned at its at the point P as sender. As a result, the two sets m prime, and what happens then? When we position the m triple prime at the point P as sender, then m prime and m double prime, the two sets fits well inside the new m set m triple prime, which is as shown in the figure. You can understand that clearly from the figure, from the last figure, which is given in figure 4. The area of m triple prime is also 4 times that of either m prime or m double prime, and it also covers. Also, we can say that in addition to that, we can say that it covers 2n minus 1. Clearly, it covers at least 2n minus 1 lattice points. But of these 2n minus 1 lattice points, if we exclude that special case of lattice points is shared by both lattice points, which is shared by both sets, both Minkowski sets m prime and m double prime, you can say that excluding that common lattice point, you can say that there is n minus 1 and n minus 1, n minus 1 in one set and n minus 1 in other set. So if we properly pair these lattice points, you know that one lattice point in one M set has corresponding lattice point in the other set. So you can pair these corresponding lattice points to obtain how many pairs. You can obtain n minus 1 pairs of lattice points. In addition to that, one shared lattice point is there. But anyway, we can say that clearly we can say that there exists n minus 1 lattice points shared by n minus 1 pairs of lattice points altogether. At least there exists at least n minus 1 pairs of lattice points altogether, which belong to the M sets M prime and M double prime. You know, how do we get it further? Again we can explain it that there exists n minus 1 lattice points belonging to this set. Corresponding lattice points are there in belong to this set M double prime, belong to the set M double prime, and if you pair them, if we pair Q prime here with Q double prime, then we get the pair Q prime Q double prime. Similarly, you can pair all other lattice points, and then in total n minus 1 pairs of lattice points will be there. But you have to exclude the case of the point P, which is shared by the Minkowski sets M prime and M double prime, and also since all of these points belong to the bigger M set, they are well inside the bigger M set, we can now make a statement about that bigger M set, that these lattice points there exist n minus 1 pairs of lattice point inside the M set having area 4A. Thus we have we can come to the conclusion part of the result. Since we have got that idea, and we can this way, even though this is the sender, since even though the given set, but at this point you have to remember that the given M set, the original M set has area 4A. It was but actually centered at the origin, but it is not at that position. It can cover n minus 1 pairs of lattice points. It can actually be translated to somewhere to some suitable position on the plane. That given M set which is centered at origin can be translated to some position, some suitable position to cover. At that position it can cover to n minus 1 pairs of lattice points. Since it can cover n minus 1 lattice points at that position, you can say that the considered lattice, or the given given M set, the given M set can cover n minus 1 pairs. It's actually the definition. You can refer the definition of covering of lattice points by a geometrical shape. From that definition, it is clear that we can say in this case of the given M set, which has area 4A, can cover n minus 1 pairs of lattice points. Okay, thank you, and this is the end of the video. Okay, thank you.